Hi, my name is Mr. Mal and higher physics is my business. And our business tonight is to go over the next set of questions from the 2016 higher physics paper. That will be questions number 11 to questions number 15. So let's get about our business and start the questions. Question 11 of the 2016 multiple choice paper in physics is all about the photoelectric effect. We're given three metals and we're given their corresponding threshold frequencies. We're told that the radiation of frequency 6.3 times 10 to the power 14 Hz is incident on the surface of each metal. And we have to decide which metals do photoelectric emission occur. Photoelectric emission is when electrons are knocked off the surface of the metal. In order to do that, the incoming photon must have a minimum amount of energy to do that. Remember from the revision that the energy of a photon depends on its frequency. So we have E equals hf. H is Planck's constant and f is the frequency of the photon. So the frequency of the photon will give it its energy. Bigger the frequency, more energetic photon, more capable of knocking electrons off a metal surface. Now, what about this work function of a metal? Well, the work function of a metal is given by the expression hf naught. Now hf naught is the minimum energy a photon will need in order to knock an electron off from the surface of the metal. It's the minimum energy required to do that. E equals hf naught, and we don't call it E, we call it the work function. Now if we can isolate f naught, we have the following. F naught is called the threshold frequency. Now below this frequency, if a photon has got a frequency below this certain frequency called threshold frequency, it's not going to knock the electrons off from that metal surface. So let's take a look at the table and see what we've got. We know that the incoming frequency of the photon is given by 6.3 times 10 to the power 14 Hertz. Now, if we look at sodium, we can see the threshold frequency is 4.4 times 10 to the power 14 Hertz. So the incoming photon has got a higher frequency needed to knock the electron off. So therefore, for sodium, electrons will be knocked off the surface of metal with this photon. Now let's look at potassium. Potassium's got a threshold frequency of 5.4 times 10 to the power 14 Hertz. Once again, the incoming photon has a frequency bigger than that threshold frequency. So therefore, electrons will be knocked off the plate, knocked off the surface of potassium. Zinc, on the other hand, has got a threshold frequency of 6.9 times 10 to the power 14 Hertz. Now that threshold frequency is greater than the incoming photon's frequency. So that incoming photon will not have enough energy to knock the electron off a surface of zinc. So we've got 2 out of 3, and our answer to that one would be sodium and potassium. So our answer would be D. Now you can pause the little film and you can copy down these following notes into your revision notebook and learn them. Good question. Question 12 of the Higher Physics 2016 multiple choice paper is still on the photoelectric effect, and this question requires you to do a wee bit of calculation. We're told that radiation of frequency 9 times 10 to the power 15 Hz is incident on a clean metal surface. The maximum kinetic energy of the photoelectron ejected from the surface is given as 5.70 times 10 to minus 18 joules. And we are required to find the work function of the metal. Now remember what we did in the last question. The work function of the metal is the minimum amount of energy needed to eject the electron from the metal surface. So any photon which comes in to the metal surface will carry energy E equals hf. Now we can think of the metal surface as a well, like this, and the electron down the bottom like that. And in order to escape the metal surface, the electron needs to have given to it an amount of energy called the work function, which is hf naught, f naught being the threshold frequency. Now that's what we're after to find. We are asked to find this work function, hf naught. So let's do a wee bit of calculation and let's see what's going on here. First of all, let's work out the energy of the photon coming in. Now that should be quite straightforward because we know Planck's constant, so we know the frequency of the photon. So the energy of the photon, E, equals Planck's constant, H, which we know is 6.63. You'll find this in the data book. 6.63 times 10 to the minus 34 joule seconds. I'll leave out the units for the moment. So we move the photon out of the way now and then multiply it by the frequency of the photon. And the frequency of the photon is 9 times 10 to the power 15. 9.00 times 10 to the power 15. Leave the units out for the moment. So the energy of the photon, we work it out, is going to be 5.97 times 10 to the minus 18 joules. So that's going to be the energy of this incoming photon. Now we're also told that the kinetic energy of the maximum kinetic energy, of the photoelectron emitted is given a certain value. So the electron is emitted up here, knocked off the surface, and that's going to have this kinetic energy. It's going to have a kinetic energy of 5.70 times 10 to the minus 18 joules. So some of the energy from the incoming photon has been spent on the work function in order to get it out of the well in the first place. So to find the work function is quite a simple little equation. The work function HF naught is equal to the energy which the photon came in with, and you subtract its kinetic energy, its maximum kinetic energy, which we'll call EK. It's a bit like being an accountant. So the energy of the photon that came in, we worked out, was 5.97 times 10 to the minus 18. And we take away the kinetic energy that it had, 5.70 times 10 to the power minus 18. And they're all joules, remember. So that's going to equal, if we do the calculation, it's going to give us an answer of 2.70 times 10 to the minus 19 joules. That's if we can do some rounding up here. So it's spent that amount of energy to get out of the well, if we can think of it that way. That's the work function. So we've checked our answers, and our nearest answer 2.67. So our answer will be 2.67 times 10 minus 19 joules once you do a bit of rounding. So the answer to that question will be number A, or letter A. So just to recap again, the energy of the photon coming in will spend some of its energy in escaping from the metal surface. And we can imagine the metal surface to be like a kind of box or a well like that, and the electron will be sitting at the bottom of that well. So the photon comes in, the electron absorbs the energy or total energy from the photon, and any excess energy it has after it's spent getting out the well will appear as kinetic energy. Question 13 of the 2016 higher multiple choice paper is about the diffraction grating. There's the usual diagram we have of it. Remember, we're looking down on the diagram. The monochromatic light is coming in here. There's the diffraction grating, and there's the screen. And on the screen we have the central maximum, and then either side we have our first order maximum. Now, the first thing you do, you look up the relationship sheet to get the diffraction equation. And there's the diffraction equation there. N lambda equals d sine theta. N is the order of the particular maximum you're looking at. Lambda is obviously the wavelength. D is the slit spacing, and sine theta is the angle between the central maximum and the first order one. So we're very careful here because that's the angle we're looking at here, which we have to change to 18 degrees. That's the angle between the central maximum and the first order one. So, like every other calculation problem, it's better to put down a list, and we do that as follows. In the first instance, we have got n, and n is going to be equal to 1 because that's the first order that we're looking at. N equals 1. What's the value of the wavelength? The wavelength is 633 nanometers, and right away we can change that to 633 times 10 to the minus 9 of a metre. Remember, 1 nanometre is 10 to the minus 9. Now, D is the separation of the slits. That is what we're after. And think of the separation of the slits like the gap between the rungs of a fence. That's what the diffraction grating really is. Now, what's the angle? Well, we did make our first adjustment. The angle is not 36, but it's 18 degrees. So we have to work out sine of 18 degrees. I'll put that in a little bracket for you to work that one out. Okay, n lambda d sine theta, if you do your wee bit of rearranging, we have then that d has got to be equal to n lambda divided by sine theta. So all we have to do really now is plug in our numbers in the usual fashion. N being 1 multiplied by 633 times 10 to the minus 9. Make sure that's in a bracket. And divide that by sine theta, which is going to be sine of 18 degrees. Now, if you do that in your calculator, you should get an answer of 2.05 times 10 to the minus 6 meters. That is the gap between each of the lines in the diffraction grating. That's the actual little small gap we call D. So we check our answer, and it's got to be answer C. So answer C for question 13. Take a wee minute to look over that question again. Stop the movie whenever you wanted to, and make sure you can work out this bread and butter calculation to calculate anything to do with the diffraction equation. Question 14 of the 2016 higher multiple choice paper is one to do with refraction of light. It says light travels from glass to air. I'm going to stop there. Light travels from glass to air. I'm going to issue a warning here because usually it's always from air to glass. So be careful. It says light travels from glass to air. Which row in the table shows what happens to the speed, frequency and wavelength of the light as it travels from glass into air? And in order to do this question, you have to study that brilliant website PHET, and the website has a fantastic simulation shown here like that. There is the simulation for it. You can see that we have got a laser light here, and this is going to be glass, and it's shining from glass into air. Now you can change these about if you wish by doing that little button there, by changing it to air and changing this to glass. But our question is all about a laser beam coming from glass into the air. And this is what happens. Now you can see what happens to the wavelength of the light. First of all, we have the light coming in, there's the normal, and we see we have a small wavelength. And then once it goes out of the glass into the air, it's going to have a bigger wavelength. So right away, we're going to have a bigger wavelength. Now, once we ascertain that, the next thing we've got to try and figure out is what's going to be the speed. And the PHET site has got a fantastic little speed monitor here. So we put this onto the waves here. We can see that in the glass, the speed of light, speed of the wave, is 0.67 c, which means 0.67 times the speed of light. Now, what happens when the ray of light comes out of the glass and into the air? Well, we're back to the speed of light. So the speed of light increases. So we have the wavelength increasing, we have the speed increasing, but what happens to the frequency? Well, if you count the number of waves passing by at this point here, and then go down here and count the number of waves passing by, you'll find out that the frequency doesn't change. So when you've got a ray of light coming from glass into air or air into glass, the frequency does not change. It's only the wavelength, the speed, and you can see in this diagram the direction. We're not asking about direction here, but you can see if we go from glass into air that the direction of the beam actually moves away from the normal rather than closer to it. Now, I do urge you to go and do this website. It's a PHET one. I'll give you a wee link to it at the end. You'll see it appearing down the screen, and it's a fantastic website to practice these sort of equations, these sort of questions. So back to it again, we know that the speed certainly increases, and we know that the frequency stays the same, and we know that the wavelength increases. So our answer to this one looks like it's going to be letter E. The speed increases, the wavelength increases, but the frequency always stays constant. So our answer is E for that one. And remember, you can go to the PHET site, look it up on Google, PHET, and there's plenty of simulations you can go and do there. I'll give you a wee bit of link down at the bottom of the screen in a minute. Question 15 of the 2016 multiple choice higher physics paper is all about irradiance, and it's about the inverse square law. It tells you here the radiance of light from a point source is 32 watts per meter squared, at a distance of 4 meters from the source. You have now increased that distance to 16 meters from the source, and you're asked to find the new irradiance. Now, if you go and look at this little simulation here, we can do this question quite quickly without the need to resort to the equation. For example, there's our point source. Remember, the inverse square law only depends on the point source, and it's giving us a reading of 250 millivolts, which we can consider that to be the irradiance of the light. So if we're only 20 centimeters away from it, if we move away to the end, you can see that the irradiance has certainly gone down. Now, this is how I would tackle this particular problem. When we're only 20 centimeters away from the detector, we get an irradiance of 250 units. Now I can mark that down as follows. If I move this out of the way, I can do the following calculation. I can say that at a distance, and therefore their radiance, I can make up a small table. And the table is quite easy to do. There's a table like this, and like that. We don't need to resort to the equation. At a distance of 20 centimeters, we have an irradiance of 250, and we'll call that 250 units. Now, if I move the light source, the point light source, away to the end, I have moved it 100 centimeters from the detector. So we're now at 100 centimeters from the detector. And we have to find the new irradiance. Well, obviously it's going to go down to 10 units. But let's see how quickly we can do this, knowing the inverse square law. You see, I have multiplied the distance by 5. Now, according to the inverse square law, the irradiance will be divided by the square of 5, divided by 25. So 250, I'll divide that by 25, the square of 5, which is the inverse square law. And lo and behold, 250 divided by 25 does give us 10 units, which we've got here. So we can use this type of argument to answer the question in the past paper. Let's see what we can do here. We start with our usual little table, distance and irradiance, and we can make up a wee mini table like that. And all we have to do is fill in what the distance is. Well, we know at a distance of 4 meters from the source, we're told that the radiance is 32 units of a radiance. We'll mark down 32. And now we move the radiance. We've got to try to find the radiance of the light source when it's 16 meters away. So 16 meters away. Now, follow through the irradiance rule, the inverse square law. If we multiply the distance away by 4, in this case, we've gone 4 times further away, we have to divide the irradiance, not by 4, but by the square of it, 16. That's where we get this inverse square law. So 32 divided by 16 is 2 units of irradiance, and the answer will be C. Now that's a very quick way to do that, and sometimes the multiple choice you need to save some time. So it's a lot easier to do that than working through the equation, which I'll show you here in blue. I1 d1 squared equals I2 d2 squared. You see, you get a lot of 2's and 2's all over the place, and you can easily make mistakes doing that, but it still gives you the same answer, because then I2, the radiance we're looking for, if we do that, it's going to be I1 d1 squared divided by d2 squared. And all we've got to do is plug in the numbers. It's probably 6.5 dozen, but this other method does save you a bit of time. So the first irradiance would be 32, multiplied by the first distance squared, which is 16, and then we would divide that by the d2 squared, which is going to be 16, so we'd have to work out 16 times 16, so it would be 16 squared. So we can see that the answer is still going to give you 2. So there's two ways to do the inverse square law, and the inverse square law, remember, we can sum up in red here. The inverse square law is always written like that. Inverse square law is directly proportional to 1 upon the distance squared. Double the distance, you quarter the radians. Triple the distance, you 1/9 the radians. Get to know the inverse square law. Well, that was questions number 11 to 15 done from the 2016 multiple choice paper in physics. I hope it's helped your study. Go back and watch the movie a couple of times. Take the notes down a notebook of any hints I was given and keep up the study. And once again, thanks for watching.